Hello, friends. This will be a invisible me doing stuff on this whiteboard, kind of walking you through a few archetypical problems that we'll need to do. I'm going to do two separate little lectures on this. The first one's going to be on exponential growth. So this is section 1.7. And the main things we need to have to build our solutions here. There's one more coming, but these are essentially the main two frameworks. We have some function, and it is of the form some constant a times this quantity 1 plus r raised to the x power. Now, check this out. Here, the variable, the input variable, x, is the exponent. So this is very different than a polynomial function, where in a polynomial function, x is the base, and we have a power on it that's fixed. So this is kind of the flip side of all that, and these are called exponential functions. There's this first form is going to be the most useful, and the second one, the ab to the x power, is something you should be aware of. But let's just talk here a little bit about this first one. This is basically interest rate growth or population growth. Those are the two main models we're going to use it for. So if you have an investment or you have a population, which can kind of be viewed as the same thing, where the more of the stuff there is, the faster it grows. So if you have a larger investment, you gain more interest. If you have more people or critters in your population, they can reproduce faster. So let's take a look at a sample problem. I'm going to look at section 1.7, the very first problem, number one. You might want to check this out with me. And you could pause this as you see fit and back it up and whatever else you need. So we have a population numbering 11,000 organisms. So that's our initial population. And it grows by 8.5% each year. So growth rate, and that's usually going to be in percents, is 8.5% per year. Write an exponential model for the population. So we're going to go with this very first one here. And we're noting that our initial population is the number a, the constant a. So a is going to equal 11K. And the growth rate, we want to convert that into a decimal. So 8.5% converts into 0.085 as a decimal, and that's our R. So R equals 0.085. And then our model, we put it all together, and I'm going to call it P. And I'm going to get crazy here and use T instead of X because it's time that the population is changing over. So we've got P of T equals 11,000 times 1 plus 0.085 to the Tth power. And that's it. That's our model. So let's actually go ahead and do a little bit more with this. First thing I'm going to do is just simplify a little. So 11,000, and then I have 1 plus 0.0, whoops, I wanted to put those together, 1.085 T. All right, and if we sketch that out, I'll do a little tiny sketch right here. We'd see it looking something like this. Here's T, and here's our population. At time 0, so in other words, P of 0, I've got 11,000 times 1.085 to the 0th power. Anything to the 0th power is 1. So that's just 11,000, just validating that that is my initial population and that I did set the model up correctly. So at time 0, we've got 11,000 here. And we could get a couple extra points, or we could put this into a calculator. We could go to Desmos. Let's maybe do that real quick here, because I think I can do that on my board. So I'm going to enter here 11,000 times, and then I got a parenthesis, 1 point. I don't really need this parenthesis, but it's modeling what we had before. And then I'm going to raise that to the, well, it looks like Desmos wants an X here. We could do T, but I think it's going to be a lot happier if we just do this. And that is my graph. So now you don't see anything, and that's because when you look at the picture, we're seeing a very small window. We need to back out so that we can see our freaking 11,000. So see, this is crazy here. There's 11,000s right there. And it just kind of rockets up after that. So the way I've written this is not great for doing a graphical analysis. What we can do is just assume that our units are in thousands, and that's going to make this all a lot better. So let's take a look down here. Now look, see, I come down here. Isn't that nice? See, and it goes right through 11 right there. And so I can use this graph to answer some questions that we're going to do mathematically, but we have to have logarithms first. But I could ask myself, when does the population double? How long does it take for the population to double from 11,000 to 22,000? So what we have to do is just on this graph, find, let's see, will it touch it? There it is. So I need to find an output of 22,000, and I'm going to have to estimate that right now. There we go. Looks like at time is 8.5. So that's 8.5 years, because our time unit here, X, was our time variable, was in years. So 8.5 years to double. And then we could answer other questions just by looking at this graph. So let's come back to our page, and that's the simplest thing we're gonna do. Let's take a look at an investment problem. So I'm looking here now at number 5 in section 1.7, and I'm in blue apparently. So I've got $4,000 invested at an interest rate of 7% per year. So this is invested at 7% per year, and that's an insanely awesome interest rate. That's like crypto interest rates. That's crazy. Find the amount in the bank after 9 years if the interest is compounded annually, quarterly, monthly, and continuously. Okay. So we need to take that very first formula that I showed you, this one here in the blue box, and tweak it to be specific to financial investments, and specifically compounded interest. So let me look here really quick and see what notation the text is using so that we use their same notation. And oh, they don't give a shit. They don't even tell us. I'm going to give you a nice formula. So if I'm doing investment, the amount that my investment is worth at time t is equal to the initial principal invested. So here, this is my initial investment. And then that is time. So you're seeing a very similar form here. 1 plus, and then we're going to take our interest rate and divide it by the number of compoundings per year. And we'll label that. And then up here, we're going to have the number of compounding periods. So we could have n times and then the number of years. So let's put a T there. Now let me show you let me label this all. So R equals interest rate. And then N equals number of compoundings per year. And then T equals the number of years that we're letting that ride. So now we can come back to this problem. And I think here we're only looking at 1 year, but at different compounding rates. So let me get back to the deets of the problem. Cool. Yep. So back at it. So we're going to, we're leaving this in the bank for 9 years. So T is going to equal 9. P, as we already established, is 4,000. That's my initial investment. And find the amount in the bank after 9 years if it is compounded first annually, then quarterly, then monthly, and then this thing continuously. And that we're going to have a special formula for that. So amount, let's just write out what we're trying to find. In account after 9 years compounded. So the first thing here is annually. And that means we're compounding once a year. So N equals 1. And my interest rate, I'll put that up here, is 0.07. That's 7% converted to a decimal. So our formula now, the amount after 9 years is going to equal 4,000 times 1 plus our interest rate, 0.07. And that's raised to the NT. So 1 year, one compounding for 9 years. So T is 9. And then we crank that out, and I'm just going to pull up my separate little calculator here on my PC. It's hiding. So I got to come over here. Come on. Why are you hiding like that? Well, it's barfing is what it's doing. It's just not working. Let me reopen it. Calculator. Isn't it nice to just hear me ramble like this? Okie dokie. So calculator, I've got 1.07. Sorry, if you could see what my calculator is doing, it's just being a chump. 1.07. And I'm going to raise that to the 9. That's not 1.9. That is just 1 times 9. So I'm going to raise that to the 9th power. So now I've got 4,000 times this I still have to find. So times 4,000. And what we get is 7353.84. So pretty good. That's a hefty amount, although it is 9 years. It's probably even worth less than the original 4,000, given how things roll in this world. Sorry, that's very pessimistic, but true. It's true. Okay, so then our next one is probably a compounding monthly. What do we want to do here? Quarterly. So that's N equals 4. And I'm not going to actually go through all these, but I am going to show you what to do. So quarterly, because I kind of want to jump to the last one. Here we have N equals 4 compoundings a year. So how is this formula going to change? Well, the amount after 9 years is now 4,000 times 1 plus, you got to be careful and divide that interest rate by the number of compoundings. So what does compounding mean? It means they take your interest rate for the year and they divide it up into the number of compounding. So if I had a 12% interest rate for the year, compounded 12 times, I would just get 1% interest each month. You know, get 12 times a month. They're not that kind. And so let's see what else we have here. So N is 4 times 9. And so that should be a lot more. This final amount here, got to do all the calculator work, should amount to more. What is the most we could get? So they give us the next problem is compounded monthly, and then compounded daily. And then they say compounded continuously. Now, this is a thing we don't really ever see in life, but it is a way to get an upper bound on the amount of interest. So if something is compounded continuously, that means that every single instant interest is being applied. But it also means your interest rate is being spread out over every instant. So it's a very strange thing. It's a very calculus-y thing that when we can actually start talking about calculus, I would like to go into, but we're not going to do that now. Let's just work from the fact that if something is compounded continuously, the amount at time t is equal to the initial investment. So that's your initial principal. Now I'm scared about spelling principal. I think that's it. Times this number e to the RT. So now E is Euler's number. That's a super calculus-y number. It really only manifests in calculus. It's the pi of calculus. As pi is to circles, E is to calculus. This is Euler's number, not Euler's number, as many of my math majors continue to say, despite my efforts to stop them from saying that. That is Euler's number, and it's approximately 2.7, 1828, 1828, blah, 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 and it goes on and on. It's an irrational number. And it, in some ways, is giving us an upper limit on interest. That's its main use in the business world, in the finance world. So now we come back to our problem. Let's look at the parameters here. We had a P was 4,000. We are going to work this one through. Our interest rate, I think it was 7%, but I want to check. 7%, so R is 0.07. That's always got to be converted into a decimal. And then T, let's see, I think it was 9 years. So T is still the number of years. So here T equals 9. And let's see here. So yeah. All right, we're going to try this out here. So the amount after 9 years is equal to 4,000 times E to the 0.07 times 9. And let me simplify that a little before I go into the calculator. So that's 4,000 times E to the 0.63. Just doing that ahead of the game. And then let's go to calculator. Can I just grab my calculator on here? Probably. Let's just grab that. Come on, bro. Like, oh, come on. There's no calculator on here. I have to get it for fuck's sake. Oh my God. Well, let's see what this stupid 3D calculator is. No, we're not doing that. Sorry, folks. I will just go to freaking Google. Okay. Because I just want to do this computation together. Now, I don't know if you know this, but you can use Google as a calculator if things are truly desperate for you. So let's see what we had here. We had 4,000 times star, and I'm going to put E raised to, so exponent, 0.63. Let's see if this actually works. I'm a little scared. I'm a little hopeful. Oh shit, look at that. That even looks right. So we've got 7, 5, 10, 44. Let's come back. So this is 7, 5, 10, 44. So compare that to what we had when we were compounding quarterly, which was 7, 5, 7, 3, 5, 3, 84. We don't get that much more. So the other times when we're compounding monthly or daily, they're not going to give us that much more, even though it feels like they would. Now, if this rode for a lot longer, if there was a larger initial principal, then we would actually see this thing grow a lot more. It would be far more noticeable. All right, so let's see. I think that kind of gets us through the rough part of exponentials. And you should be able to get all the homework done after this. On Monday, we are going to talk about the sample exam I gave you, and in particular about this stuff, but also the cost and demand curve stuff that is in the sample exam. Check that out. Check out that example that I reference. It's example 10 in the section on lines. And I hope you're doing well. I will come out with a video for the reverse of all this, which is logarithms, as soon as possible. I'm not sure it's going to be today, but it will be in the next several days. So be well, my friends. I will see you Monday. Let me know if you need anything. I'm going to stop this video. Something. Still stopping. Bye.